Hello guys, welcome to the channel GG Physics by VG sir. So today we're going to see one very important topic, a very important concept from magnetism. Okay, so first I'll explain the concept, and after that I'll take some two three examples. Okay, so the concept that we are going to discuss today is magnetostatic pressure. Okay, so here we're calling it as magnetostatic because the current, okay, the surfaces which we are considering, okay, the bodies which we are considering, they're carrying the current which are constant. Basically, they're not varying with what time. Okay, so that's why we're calling it as magnetostatic, where the magnetic fields are like static. That means they are fixed. Okay, and because of that, some pressure being created. So that pressure we are going to calculate, similar to like what electrostatic pressure and the gravitation pressure that we have seen in like what earlier chapters, right? So let's say there is an like infinite sheet. Okay, there is an infinite sheet which is like this, carrying current. Okay, which we are seeing here. We are looking into the side view. Okay, so basically the sheet is into the plane, which is carrying a current, uniform current, which is given by current per unit length, which is given as what, K. Current per unit length given as what, K. And by using Biot-Savart's law, sorry, by using ampere circuit law, we can find the field over here. Okay, infinite sheet, so the field will be uniform. So I am not doing the derivation part here, okay, because we are not discussing that topic. So it's similar to like what electric field due to infinite sheet. The formula you guys already know, it's like sigma by what, 2 epsilon naught, due to infinite sheet, uniform electric field. Similarly, due to a infinite, okay, current carrying conduct sheet, the magnetic field produced will be what, fixed, like it's uniform. And the formula is given as, see, as the current is coming upward, okay, like you can see here, if you see, it's coming out of the plane, right? So if you use your right hand thumb rule by keeping out of the thumb, so right side the field lines will be going in what direction? Right side the field will be going in upward direction like this, and left side it will be going what, downward, right? And the magnitude I'm directly writing, which you can get by using ampere circuit law, that is mu naught k by 2, and here also what, mu naught k by 2, right? So similar to what, similar to like sigma by 2 epsilon naught, that you will be getting electric field that you will be getting due to infinite sheet, right, which is carrying a charge density of what, sigma, right? So let's say now this sheet is being placed inside a, inside in some external magnetic field. Let us consider that external magnetic field be capital B naught. Okay, so it's there in the entire region, right? So it's like there in the entire region. So left side also there will be B naught, and right side also B naught. Everywhere it will be what, B naught. Let us say the net magnetic field right side. Let me name it as what, B1, and let us name it as B2 on the left side. Okay, so now tell me what will be the net magnetic field on the left side. So that is B2, which can be written as B naught minus B naught minus, because the other due to this sheet the field is in downward direction. So B2 can be written as what, B naught minus mu naught k by 2. And similarly B1 can be written as what, so because both are getting added here, mu naught plus mu B naught plus mu naught k by 2, right? So by using these two, I'll try to find B naught in terms of B1 and B2. Similarly, I'll find K also in terms of B1 and B2. So why we are doing this, you'll understand later. Okay. So for time being, you just we are trying to derive a formula. Okay, or rather we are trying to understand a concept. And first, after understanding this concept, I'll give one two examples, and also I'll give some questions as your homework that you guys can try. Right. So as I said, first let us find B naught and B1. Okay, so if I just add these two, what will you get? B1 plus B2, which you will be getting it as what? 2B naught. So therefore, first important thing we got is b naught is nothing but b1 plus b2 by 2. That means the external magnetic field can be simply written as what? The external magnetic field can be simply written as average of whatever the magnetic field that is there on the right side and left side, right? So simply that is b1. Let's say b1 is the net field on the right side, and b2 is the net field on the right side, and b2 is the left field, net field on the left side. So just by taking average of these two, we can get what is the external field that is being present, right? And this mu naught k by 2, you need to understand this is the self, the field because of itself, right? So this we can call it a self field, and b naught is the external field. And whereas b1 and b2 are what? B1 and b2 are the net magnetic fields. So we have found external magnetic field in terms of, okay, whatever the net magnetic field that is present on either side of this sheet. Okay, so I hope it is clear. Now let us also find the current per unit length k. Let us also find the current per unit length k over here. So how to find? So these two equations are there, right? So let me just so I'm just naming these equations as 1 and 2. So earlier we have just added equation 1 and 2. Now let me do equation 2 minus equation 1, right? Let me do just equation 2 minus equation 1 that I'm writing over here. So when you do equation 2 minus equation 1, so what we will be getting? b1 minus b2, so which is equal to what? Mu naught k. So therefore I also got the value of current per unit length in terms of the net magnetic field on either side of this what? Infinite large sheet. So that is mu b1 minus b2, b1 minus b2 by mu naught, right? So this is the current per unit length in terms of the net fields, okay, in terms of the net fields that are present on either side of this either side of this infinite current carrying sheet. Okay, now, so we need to, as the concept here is, we need to find the pressure, okay, on this sheet due to this external magnetic field whatever that is present. So to understand this, okay, first to calculate pressure, let us find the force acting on this one. So to get that, so in this infinite sheet that is present over here, I'm going to take a small, okay, small element over here, okay, small element over here, which is like this. Okay, I'm going to consider a small element like this. Okay, let me take a small element like this. Okay, so small element I have taken. So the current, you can see it is coming out of the plane, right? Here dot means out of the plane. So so we have slightly tilted this figure. Okay, earlier we are just looking, okay, this manner, so we have just slightly tilted this. So the current is coming like this, and this is this y direction. Okay, this is the length dy, and let's say this is into the plane, the dx, and the magnetic field is cutting perpendicular to this one, these lines. Okay, because current is coming out of the plane, and magnetic field is like going upward, right? So magnetic field lines will be cutting perpendicular to these lines whatever that is present over here. Okay, so now let me find the force that is acting on this one. Let us find the force that is acting on this one. So let me call it as the force df. Let me call this the force df. So what will be the df? So force acting on a current carrying conductor, okay, this is nothing but what? I into dl bar cross b bar. So here you need to understand this dy is very very small. This is something similar to what? It's nothing but something similar to taking a thin wire, right? So don't get confused here. You might be thinking, so it's like an sheet, what is the formula? See, you already, you guys know what is the force that is acting on a what? Thin current carrying conductor. So this dy is like what? Infinitesimally very 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 small. Okay, this is nothing but almost equivalent to what? A thin wire, right? So this is almost equivalent to what? A thin wire. So we can simply use whatever the formula that you guys know, the current the force on a current carrying conductor, that is what? I into dl bar plus b bar. So first I wanted to know the I value, right? Sir, what is the I value? I value is nothing but K is the current per unit length, right? And what is the length of this element that we have considered here? Dy. So K dy is the I into length of the wire that we have taken, length of the conductor that we have considered. This is the length, right? Dx. So I have taken a length, so I into dl bar. Okay, already I have told ideal bar is nothing but this is the ideal bar direction, which is the current direction itself. Okay, ideal bar is this one, b bar is perpendicular to this one, so angle between that is like already 90. So simply to get this force, the magnitude is, as angle between them is 90, simply the force can be written as what, ILB. So b is nothing but the external magnetic field that we are having, b naught, right? So here the force, small force acting on that one, can be written as k b naught into dx into dy. So here if you carefully observe, this dx into dy is nothing but what, dx into dy is nothing but area of this small element that we have considered. So if I just divide, okay, this, if I take this term to the left side, so df by dx by dy is nothing but what, is nothing but the pressure, right? So therefore the pressure that is acting on this one can be simply written as what, k b naught. The pressure, the final form that we are getting is what, k b naught. Okay, this is the final formula that we are getting, k b naught. Okay, so I hope this is pretty much clear for you guys. So df is the small force that is acting on this element. Okay, and the area of this element is what, it's just like a small rectangle that we have considered. So it's nothing but what, dx into dy. So when you just divide this force by that area, you're getting the pressure. So the pressure formula that we have got is what, k b naught, right? But so I'm just changing this formula by a bit. Why? Because as I said, in the questions they might not be giving this k, or they might not be giving this external field. If these two are given, then directly the answer is kb naught. Okay, there is no doubt on this. So this is the final result. But let's say instead of this, we know the net magnetic fields. Instead of this, let's say we know the net magnetic fields on either side of the sheets. Then this formula, whatever I have got, the pressure formula kb naught, I'm going to change by a bit. So already we have k value as what, this one, and already we have b naught value as what, this one. So when you do, it's nothing but b1 minus b2 into b1 plus b2, a plus b into a minus b, so a square minus b square, right? So the pressure formula that we are getting, is what, b1 square minus b2 square by 2 mu naught. So if I just rearrange this one, so the pressure can be simply written as b1 square by 2 mu naught minus b2 square by 2 mu naught. b1 square by 2 mu naught minus b2 square by 2 mu naught. This is the final result that we have got. So this is something similar to like what, electrostatic pressure that we are getting. Okay, so later when you want to like remember this formula, you can just check the analogy that we will be getting. Okay, so the final result that we got is what, the pressure that we got is b square by b1 square by 2 mu naught minus b2 square by 2 mu naught. So here the most important thing is the pressures that are present on either side. Okay, here the most important thing is, sorry, my bad. So here most important thing is b1 b2 are what, the net magnetic fields on the either side of the what, sheet. Here b1 and b2 are the net magnetic fields that are present on either side of the sheet. So by just by using this formula, we can get what is the pressure that is experienced by that element or the sheet, whatever that is present. Okay, so any uniform current carrying like sheet or surface that we have, we can directly use this formula. Okay, so I hope this concept is pretty much clear for you guys. Now let me take up a like one two examples over here. Okay, so I'll take up one two examples over here. Then as I said, I'll also give homework for you guys. Okay, so let me take up the example over here. So this is the example number one. So let me consider a cylinder, okay, hollow cylinder, which is carrying a current I, which is carrying a total current I, in the upward direction. Okay, let's say it is carrying a current I like this on the surface. So I is the what? I is the surface current. I is the surface current. Okay. So on the surface of this cylinder, hollow cylinder, this is hollow cylinder. On the surface of the cylinder, it is carrying a uniform current of what? I on the entire surface. Okay. So now we need to find what is the pressure that is experienced by this hollow cylinder. So see, the solution part is very simple. So as we already derived the formula and we understood the concept, see inside the cylinder, we know the magnetic field here is what? The magnetic field, let me call, just take the point which is inside, let me call it as what? Point number 2, and let me call it, take a point just outside, point as what? 1. So we already know B2 inside a long hollow cylinder, the magnetic field value is what? 0. This also we can find by using what? By using ampere circuit law. Okay, again I'm not going into that. So B1 just outside the surface, which is equal to just which is present on the surface, that is mu naught I by what? 2 pi r, mu naught I by 2 pi r, right? So now as we know B1 and B2, directly I can find what? Directly I can find the pressure. So the pressure that it is going to experience, the pressure that it is going to experience is nothing but what? So it's nothing but simply B2 is already 0, so this term is 0. Simply the answer is what? B1 square by 2 mu naught. So what is B1 square? B1 square is nothing but mu naught square I square by 4 pi square r square into what? Into 2 mu naught. So the answer that we are going to get is P equal to mu naught I square, mu naught I square, mu naught I square by mu naught I square by mu naught got cancelled, 8 pi square r square, right? So this is the pressure that we are getting on the surface of this hollow cylinder, which is carrying a uniform current of what? Uniform current of I. Okay, so this one we have got directly by using the formula. Similarly, I can take up one more example if you want. So another example I can give is this one. So let me consider there are two cylinders. Okay, let's say there are two cylinders like this. Let me consider there are two cylinders like this. Okay, let's say this inner cylinder is carrying a uniform current density of uniform current of I1 hollow cylinders. This outer cylinder is carrying a what? Uniform current of I2 only on the surface. And let's say the inner radius is R1. Okay, inner radius is R1 and this outer radius is R2. Inner radius is out1 and outer radius is what? R2. Now they might ask you to find what is the pressure on this surface. Okay, so simply what you need to do is that simply you just need to take 2 points just on either side of the surface. Let me consider this is point number 1 and this is point number 2. Now you guys need to understand, okay, at point 1 the field is not 0, right? At point 1 the field is not 0. Why? Because due to this outer cylinder the field is 0 over here, magnetic field, but due to this inner cylinder we'll have a field over here, right? So let me write what are the B1 value. So what is the B1 value, sir? So B1 value is nothing but it will be only because of what? At the point 1 it will be only because of the inner cylinder, which is nothing but mu naught I1 by, it is at a distance of what? 2 pi r2. And similarly B2 is equal to what? B2, it is the outside point for the, it's the outside point for both the cylinders, right? It's the outside point for both the cylinders. Understood, right? So it will be like what? Both the current will be added over here. So because the current directions is same, so if it is different, then they'll get subtracted. So mu naught into I1 plus I2, mu naught into I1 plus I2 by 2 pi R2. So once you guys know the values of B1 and B2, right? So the pressure for the outer surface, pressure on the outer cylinder, I can say, outer cylinder equal to what? Equal to simply, I'll use the formula. Which side the magnetic field is more? Outside it is more, right? So when outside is more than inside, so you can see that it is getting what? Compressed. Okay, So it is going to get what? Compressed. So in the previous one also you can see inside it is 0, and outside this is the field. So outside is more than inside means it will try to get what? Compressed. So here I can just use the formula directly, as outside one is more. Okay, so outside one is more, simply I can write b2 square minus b1 square by 2 mu naught. Okay, similarly if you want you can find the pressure that is present on the inner cylinder as well. Pressure on the inner cylinder also you guys can find. Okay, so for the inner cylinder, if I consider two more points, what are those points? Let us take this point as what? Let's say 3, this point as what? 4. So I can simply write. Okay, so you guys can clearly see pressure at magnetic field at 4 will be more, right? So the value can be written as b 4 square minus b3 square by 2 mu naught. Right, sir, you have only given the values of b1 and b2. So what about b3 and b4? B3 is inside for like both the cylinders, so b3 equal to 0, and b4 it will be only because of what? It will be only because of inner cylinder, so which will be mu naught I1 by I1 by 2 pi R1. So these are the values of B3 and B4. Once you guys know the values of B3 and B4, right? Once you know the values of B3 and B4, you guys can simply substitute in the formula that I have written there, and easily are going to get the answer, right? So we'll just directly substitute this over here and we'll get the answer. So I hope the concept is clear for you guys, and also the examples are also pretty much clear for you. Okay, now the homework part for you guys is, okay, so based on this concept there are like questions that are given in both irido as well as pathfinder. So irido, the numbers are like 3.59, like this. Some 5 6 questions are given in the irido. Okay, you guys can check after going through this concept. Okay, once you guys can go and try to solve these questions, then you'll have the pretty much confidence about this concept, magnetostatic pressure. Okay, so often by looking into those questions, no, like so people they'll get confused of like what approach you need to follow and how to tackle those questions. So once you understand this concept, okay, this formula, finding the net pressure on either side and using this formula, so directly you guys can get the answer. Okay, so if you want to understand this better, okay, without using this formula also you guys can try. Okay, this one. So like the idea goes like this. Okay, so if you want I'll just explain that also you guys can try the example one that I explained, right? So let us consider, let's say this is the top view. I'll just give an idea so that you guys can try this method as well, then you'll get better understanding, right? So let's say this is the top view of this one. So it is carrying current in what? Out of the plane like this. So in the entire region it's uh, carrying the what? Current out of the plane. Now you guys need to understand b inside is what? B in, this is b in, b in is out. So b in is 0, inside magnetic field is 0, and b outside is what? Mu naught I by 2 pi r you will be getting. So let's say I wanted to find force on this small element that I've considered here. See, the element that I have highlighted. So I wanted to find the force that is acting on this small element, and divided by that area we'll be getting the what? Pressure. So here you need to understand, so to find force acting on that one, we cannot consider the fields, okay, the net fields that are present. It is something similar to in electrostatics. If you, okay, clearly observe, when I calculate electrostatic pressure, so the outside any conductor, the field value is given as what? Sigma by what? Epsilon naught. But you need to in outside any conductor. But the most important thing is when you take small element over there, the entire the net electric field, that sigma by epsilon that you are getting, is it is because of the small element that we are taking, and the remaining thing, it is because of the what? Entire like remaining conductor. Similarly here, whatever the net fields that we are getting inside as 0 and outside as mu naught I by 2 2 pi r, it is because of this small element, as well as this entire like what are the conductor that is remaining. So that means to find what is the external field due to these two, okay, you guys need to understand it's not equal to b out or it's not equal to b in. So it's like I guess you got an pretty much clear idea as I give the clear analogy between whatever you will be getting to find electrostatic pressure. The same thing you can do over here. Only thing that you need to understand and remember is the b out and b in, the formulas that you are writing directly, it is because of this small element and the entire element. But when you wanted to find the force, when you wanted to find force on this element, obviously the magnetic field of itself cannot apply any force on top of that element that you are considering. So on that element the force will be because of the remaining field that you are remaining electric magnetic field that we will be getting. So we cannot take directly the values or the formulas that we know outside the cylinder and inside the cylinder. Okay, so the same way whatever we are doing in electrostatics, here also we will be getting half of that whatever we will be getting uh, by using the formula. Okay, so I hope you understood the like idea that I have given here. Okay, I am not doing the entire derivation over here because the video will become again little bit lengthy. So I have given a nice idea by keeping a nice analogy with what electrostatic pressure that we will be doing. So once you do that, again you're going to get whatever the formula that we have derived here. Okay, then you will get you'll be getting more and more like clarity and understanding over what we are doing. Okay, and what is this formula and how we are using it. Okay, without this formula also, by the method that I have told here, we can find. But every time deriving like this, it will take some time, right? So as I said, it's a standard concept and important result, and it will be valid for any uniform current carrying sheets. Okay, so by using this formula, you can directly get the answers. As I said, you guys can also uh, check with these questions whatever that is given in irido, and also in pathfinder also you can find 2 to 3 questions based on this magnetostatic pressure, right? So I hope this concept is pretty much clear for you guys. So once again, go through this video and try to derive these concepts on your own. Then you will be getting better understanding once you get idea, right? So then solving those questions will become very very easy. And yeah, so then it will be take work for you whenever you want to solve these type of questions based on magnetostatic pressure. So I hope this video is very helpful for you in mastering the concept of what magnetostatic pressure. Okay, so thank you guys. Please like the video, and if possible share to your friends. Okay, just so that they will also get to know about this channel and they will also get benefited from this channel, right? Okay, thank you guys. Bye bye.